Hi there, Mr. Sutton here, bringing you the AB Calculus Derivative Extra Practice number 7 solutions. On this problem, I'm trying to find the derivative of this function. Now, before we go ahead and launch into a product rule here, because we do have a product, it's worth noting that we can rewrite cotan of 2x as cosine of 2x over sine of 2x. And this sine of 2x and this sine of 2x can cancel out. So really, this is just y equals cosine of 2x, which is just a small chain rule. This is going to be negative sine of 2x times the tail of 2, giving us negative 2 sine of 2x for our final answer. To find the derivative of this function, we're going to have to use the product rule. So I've got u prime v plus uv prime. Here's my box and ribbon. And my first factor, that's going to be this x to the 43rd plus 6 to the 5th power. And the other factor, we have ln of x squared, which, using log rules, I'm actually going to pop out that 2 and write that as 2 ln of x. That'll save me a little bit of a chain rule. All right, so for this first one, I can't avoid the chain rule. I've got something to the 5th power. Derivative of that's going to be 5 times the something, x to the 43rd plus 6, to the 4th power. Now we multiply by the derivative of this inner function, which is going to be 43x to the 42nd, and that's 6 a constant, so 6 is going away. All right. Over here we have derivative of 2 ln of x. That's just going to be 2 over x. Multiplying it out with the ribbon now, we've got all the stuff in the lower left here times 2 ln of x. There we go. And we're going to be adding to that the other way on the ribbon here. We've got 2, we have an x to the 43rd plus 6 to the 5th. We're dividing all that by x. Or you could say this times 2 over x. Either way doesn't really matter. So there, in one form or another, is one possible answer. To find the derivative on this problem, at some point we're probably going to need a quotient rule, but we can reduce the amount of work we're going to have to do on this in the beginning if we simplify this a little bit upstairs. Tan of x, for example, is really sine over cosine of x. So these cosines can cancel, and we can just write this as sine of x over e to the x ln of x. Still going to be a bit of a beast to deal with, but less of a beast, I guess. So let's bust out the quotient rule now. U prime v minus uv prime over v squared. And we'll use the box and ribbon to help keep things organized, and we're going to need it on this one. So my numerator, I've got sine of x going there. In the denominator, that's e to the x ln of x. No way to really simplify that. And now the derivatives of those, sine of x, that's going to be cosine of x for the derivative. And e to the x ln of x, this is a product rule. So we're actually going to have to use the box and ribbon again, this time in product rule form. So there's our product rule. U prime v plus uv prime. That's the pattern we'll be following for this derivative down here. So setting up this box and ribbon, we have e to the x and ln of x. Derivatives are e to the x and 1 over x. So now multiplying this out with the ribbon, we have e to the x times ln of x. Plus, we're going to have e to the x times 1 over x, or e to the x over x, either of those. And now we're going to take one step backwards and use the ribbon on this box to fill in this overall structure here. So for the overall quotient rule now, we've got cosine of x times e to the x ln of x, and that's all on top of a big old fraction here. And going the other way now, we're doing minus sine of x times parentheses, all of that stuff, all over e to the x ln of x squared. On this problem, to take this derivative, we're going to need a chain rule on this first term. Now this other term, this minus ln of 8, that fortunately is just a constant, so the derivative of that stuff is just going to be 0. So really it's this first term we're going to focus on. So using the chain rule, we've really got 8 to the something going on here as the outer function. Derivative of that is going to be 8 to the something ln of 8, so 8 to the arctan of 8x ln of 8. Next, we have to take the derivative of arctan of 8x. Well, that's arctan of something. That's another chain rule. So that's going to be 1 over something squared plus 1. So 1 over 8x quantity squared plus 1. Finally, we multiply by the derivative of 8x, the innermost function, and that is just 8. On this problem, as tempting as it is to try to simplify and cancel out this tan and this arctan before taking the derivative, we actually can't do that, because this is not tan of arctan, it's tan to the arctan. We've got a variable in the base and the exponent. That means we have to use logarithmic differentiation. So I'll start by taking the ln of both sides. That leaves me with ln of y on the left side, and on the right side, taking ln causes the arctan exponent to pop out and join us on the ground level here. And next to that, we have the ln of the base, tan of x. So now using implicit differentiation, on the left side, we have 1 over y times dy over dx. Y is an inner function of y, so we have to use the chain rule there. On the right side, we have a product rule, so I'm going to negotiate that with my box and ribbon. Arctan of x, that's one of our factors. The other is ln of tan of x. Derivative of arctan, that's going to be 1 over x squared plus 1. Ln of tan of x, that is really ln of something, using a chain rule here. So that's going to be 1 over the something, 1 over tan x, times the derivative of the something, times secant squared of x. Multiplying it out now with the ribbon, we've got 1 over x squared plus 1 times ln of tan of x, and I'll just move that into the numerator of that fraction. And then going the other way, we're going to have arctan of x, secant squared of x, all of that over tan x. And now we have to still isolate dy over dx. I can do that by multiplying both sides by y. So I've got y times all of the stuff on the right side in a parentheses. And if you wanted to replace y with this original function here to get it completely in terms of x, that's certainly an option. They didn't say you had to do that on this problem, but there might be other times when you want to, so there's an alternate solution. On this problem, at least for part of it, I'm going to have to use the chain rule to differentiate here. So I've got secant of something, that's the outer function on this first term. Derivative of secant of something is going to be secant of something times tan of something. So secant of arcsine times tan of arcsine of 2x. And then, let's see here, we still have to multiply by the derivative of arcsine of 2x. So that's going to be, let's see, this is really arcsine of something. So that's going to be 1 over the square root of 1 minus something squared, like so. And finally, we have to multiply by the derivative of 2x itself. So that's a 2 there. So that's all just that first term taking the derivative. Now don't forget we still have this plus 6x from the original function, but the derivative of that's not so bad. That's just going to be a plus 6 on the end there. On this problem, it's initially looking like we have a variable in our base and exponent, which would indicate that we need logarithmic differentiation, and you could go that route. But it's actually much easier if you just, since we're ln'ing this x to the power, we just pop out that power of secant squared of 5x out in front using log rules. So I can rewrite this as secant squared of 5x times ln of x, and now instead of using logarithmic differentiation, I can just use the product rule, u prime v plus uv prime. Let me set up the box and ribbon for that. So I have secant squared of 5x in one of these, and the other is going to be my other factor, ln of x. Derivatives now, this is going to be a big chain rule right here. We've got something squared as the outer function, so that's going to be 2 times secant of 5x. Now we have to multiply by the derivative of secant itself. That's going to be secant of 5x tan of 5x. And then finally multiply by the derivative of 5x, which is 5. Over here, ln of x, not as much going on there. This is just going to be 1 over x when you take that derivative. Multiplying it back out now using the ribbon, we've got all the stuff in the lower left that I'm not going to repeat, times ln of x. So all that stuff, ln of x. Plus, we have secant squared of 5x, and I'll just write that over 1. Or actually, we'll do times 1 over x. Doesn't really take that much space to write that. So there it is. Product rule, derivative, done. On this fun problem, we have a whole bunch of e's and pi's in different combinations. So let's go through these one at a time here. Going from the left here, taking the derivative, pi e to the x. Well, the derivative of e to the x is just e to the x, and pi is along for the ride. So that is still pi e to the x when I take the derivative of that. Over here, well, now we have the pi in the exponent, so a little bit different. This is going to be e to the pi x times the derivative of pi x, which is pi. So this is going to end up being pi e to the pi x because of the chain rule. And now this last one, x to the pi times e, well, this is x to a constant. So we're going to actually use the power rule here. This is going to be pi e times x to the pi e minus 1. For this problem, to take the derivative, because we can't isolate y, we're going to use implicit differentiation. So whenever I take the derivative of something with a y, I'm just going to treat y as an inner function of x and multiply by a tail of dy over dx, the derivative of y. All right, so let's go ahead and take those derivatives. On the left side, we immediately get hit with a product rule. So let me get the box and ribbon out here. We have factors of 2x squared and y cubed. Derivative of 2x squared is 4x. Y cubed's derivative is going to be 3y squared times dy over dx. Again, we're using the chain rule, treating y as its own function. And then multiplying that out with the ribbon, we've got 4x y cubed plus, let's see, combine these here. This will be 2 times 3 is 6, x squared y cubed dy over dx. And then we have the other side of the equation, which is just y, so we can write equals derivative of that, which is dy over dx. Okay, let's get all the dy over dx's on one side and the other stuff on the other side. We have this 6x squared y squared dy over dx. That can stay on the left side. This dy over dx, I'm going to subtract to get it over to the left side. And 4xy cubed, I'm subtracting that to move it over to the right side. At this point, I can factor out a dy over dx. That leaves me with 6x squared y squared minus 1 on the left side. No change on the right. But now, to get dy over dx by itself, I have to divide this negative 4x cubed by this whole parentheses here, and that ends up giving me my derivative. To find the derivative of this function, I'm going to have to use the chain rule. My outer function is cosecant of something. Derivative of that is going to be negative cosecant of the something, cotan of the something being 6x to the 6 to the x squared. So there's a negative cosecant of that, cotan of that. That's all one big outer derivative. Next, we move on to taking the derivative of the next function in. The next function in is another chain rule. This is going to be 6 to the something. Well, the derivative of that is going to be 6 to the something, 6 to the x squared, times ln of 6. And then finally, we need the derivative of the innermost function, x squared. So that's just going to be 2x. For this problem, we could potentially have a nasty-looking product rule staring us in the face here, along with some chain rules. But one way to avoid that, you might remember there's a trig identity that has cotan squared and cosecant squared in it. Specifically, cotan squared plus 1 equals cosecant squared. If we rearrange this, we can get this expression here by subtracting cosecant squared from both sides and then subtracting 1 to the other side. So basically rearrange it to look like this. And with this, we see that cotan squared minus cosecant squared of an angle actually is equivalent to negative 1. So we're going to replace this whole thing here with just negative 1, and we still have that x squared there. So taking this derivative, the derivative of basically negative x squared, that's going to be negative 2x.